In this video, we're going to tackle another foundational system design challenge, building a key value store. Key value stores are at the heart of modern distributed systems, powering everything from caching layers to metadata storage, session management, and even some recommendation systems. While the concept sounds simple, mapping a key to a value, the real challenge lies in designing a system that can handle huge volumes of traffic, automatically scale, survive failures, and serve requests with ultra-low latency. In this session, we'll break down the essential design principles behind a robust key value store, exploring trade-offs, replication strategies, failure recovery, consistency models, and more. By the end, you'll have a strong mental model of how systems like Amazon Dynamo, Cassandra, and others are built under the hood. Let's jump in by starting with the problem statement. Design a key value store with key value pairs where keys and values can be strings, lists, objects, etc. When designing a key value store, especially one that powers high-traffic systems, we need to focus on several critical requirements to ensure performance and reliability. Small to medium object size. Most key value pairs are relatively small, typically less than 10 kilobyte. However, the system should still support larger values occasionally, such as images or JSON blobs. This means our architecture should be optimized for small object reads, writes, but flexible enough to handle bulkier data. High availability downtime is unacceptable for modern services. The key value store must support high availability through replication, failover mechanisms, and possibly multi-region deployments to survive node or data center failures without service interruption. High scalability. The system should seamlessly support growth in traffic and data volume. It must scale horizontally, adding more nodes to handle increasing loads, without major reconfiguration or downtime. Automatic scaling. Beyond manual scaling, we want the system to monitor traffic and load patterns and scale resources accordingly. This includes automatic shard rebalancing and dynamic partition management. Tunable consistency. Not all use cases require strong consistency. For example, reading slightly stale data is acceptable in many caching layers. The system should support tunable consistency levels, ranging from eventual to strong, so developers can choose the trade-off between performance and correctness per operation. Low latency. Fast response times are essential for good user experience. The system must support low latency reads and writes, ideally under a few milliseconds. This requires efficient data access paths, caching, and minimal network hops. In summary, the key value store needs to be fast, fault-tolerant, elastic, and adaptable to different use cases, which makes it a foundational component in scalable system architectures. There's one important theorem we need to discuss first. Let's now talk about the CAP theorem, which is a fundamental principle when designing distributed systems like a key value store. The CAP theorem states that a distributed system cannot simultaneously guarantee all three of the following properties. Consistency. This means that all nodes in the system see the same data at the same time. If a client writes a value to a key, any read immediately after should return that same value. Availability. Every client request receives a non-error response, even if some nodes in the system are down. The key here is that the system remains operational for all requests. Partition tolerance. The system can continue operating despite network failures or partitions that prevent some nodes from communicating with others. In real-world distributed systems, network partitions are unavoidable, so partition tolerance is usually non-negotiable. Since we can only pick two out of these three, systems make trade-offs. A CP, consistency plus partition tolerance system, will sacrifice availability in the face of a network partition. For example, during a partition, it might block writes to maintain consistency, leading to unavailability for some users. An AP, availability plus partition tolerance, system will sacrifice consistency. It continues to serve read and write requests during a partition, even though it might return stale or inconsistent data temporarily. Understanding these trade-offs helps us decide the architecture and design goals of our key-value store, especially when we are optimizing for scenarios like real-time updates versus system uptime. In a scalable key-value store, efficient data partitioning and replication are critical to ensuring high availability, fault tolerance, and load balancing. First, let's talk about data partitioning. We distribute our data evenly across multiple servers using consistent hashing. This technique helps ensure that the keys are spread uniformly over the available nodes, and when servers are added or removed, only a small subset of keys need to be moved. This minimizes rebalancing and allows the system to scale automatically and seamlessly. Now, on to replication. To ensure availability and fault tolerance, we replicate each piece of data asynchronously across multiple servers, typically n replicas. When a key is inserted, we hash it to a position on the ring. Then we move clockwise around the ring and store replicas on the first n unique servers encountered. This means even if one or two servers go down, the data can still be retrieved from other replicas. This combination of consistent hashing and replication allows us to scale out and ensure high availability without compromising too much on performance. We'll go into how these mechanisms interact with consistency models in a later slide, especially in the context of CAP theorem trade-offs. When building a distributed key-value store, one of the biggest challenges we face is balancing consistency, availability, and latency. This is where the quorum-based consistency model comes into play. Replication parameters. We denote three key parameters to control consistency and availability. N is the total number of replicas for each piece of data. W is the minimum number of replicas that must acknowledge a write for it to be considered successful. R is the number of replicas that must return a value for a read operation to be considered successful. Latency versus consistency trade-off. The beauty of this model lies in its tunability. We can adjust W and R depending on our application's need for performance versus consistency. If we set W entry 1 or R entry 1, we get low latency because we only wait for one replica to respond. But this could lead to stale reads or data loss in failure scenarios. If we want strong consistency, we make sure that W plus RN. This guarantees that at least one replica that received the write is included in any subsequent read quorum, ensuring the most up-to-date value is returned. Example. For example, if n nishar 3 setting W tishar 2 and R chishar 2 means that both read and write operations will involve two replicas. Since W plus R pshisham 4 3, we achieve strong consistency, but this comes at the cost of higher latency and potential availability loss if nodes are slow or down. This quorum-based model gives system designers the flexibility to dial up or down on consistency and latency based on their application needs, whether it's a financial application demanding strong consistency or a social feed that can tolerate eventual consistency for better performance. In distributed key-value stores, inconsistency can arise due to network partitions or asynchronous replication. To handle this, we use vector clocks as a versioning mechanism. A vector clock is essentially metadata that keeps track of the history of updates for a data item across different servers. It's represented as D, S1, V1, S2, V2, I, SN, VN. Here, D is the data item, S1 to SEN are the server identifiers, and V1 to VN are their respective version counters. Whenever a server SCI writes a new version of data D, it does one of two things. If SCI VI already exists in the vector clock, it increments VI. If this is the first time SCI is writing, it adds a new entry, SCI 1. Now, to determine whether one version is an update of another, or if it's a conflicting sibling, we compare vector clocks. If every counter in version Y is greater than or equal to the corresponding one in version X, we say X is an ancestor of Y. This means no conflict. It's just a newer version. If some counters in Y are less than in X and vice versa, then they are siblings. This signals a conflict. Both versions must be preserved and later reconciled, either automatically or manually. This versioning model gives us the ability to reason about causality and handle divergent updates gracefully without blindly overwriting data or losing intermediate updates. To build a highly available and fault-tolerant key-value store, it's crucial to handle different kinds of failures gracefully. This includes temporary outages, network partitions, and permanent node loss. Let's look at the techniques we use. 1. Gossip protocol for failure detection. Every node keeps a membership list with each node's ID and a heartbeat counter. Nodes increment their own heartbeat counters periodically to indicate that they're alive. These heartbeats are propagated using a gossip-style protocol where each node sends its membership list to random peers at regular intervals. Upon receiving a heartbeat, nodes update their membership list to keep it current. If a node's heartbeat hasn't increased beyond a set threshold, it's marked as down. This decentralized, probabilistic method allows us to detect failures without needing a central coordinator and ensures the system remains scalable and fault-tolerant. 2. Sloppy quorum and hinted handoff. To maintain availability during failures, we use a sloppy quorum approach. Rather than writing only to the exact n nodes that are responsible for a key on the hash ring, we select the first W healthy nodes for writes and R for reads. If one of the primary replicas is down, a nearby healthy node temporarily handles the write. Once the original node comes back online, these changes, referred to as hints, are handed back, a process known as hinted handoff. This allows the system to accept reads and writes even during partial outages, helping us meet high availability requirements. 3. What if a replica is permanently unavailable? In such cases, we ensure eventual consistency using anti-entropy mechanisms. Anti-entropy involves comparing each piece of data between replicas and updating them with the most recent version. To do this efficiently, we use Merkle trees, a hash-based data structure. Leaf nodes represent chunks of data and are hashed. Internal nodes are labeled with hashes of their children. By comparing root hashes of two replicas, we can detect if they differ. If they do, we recursively compare their children to locate and resolve only the differing data. This drastically reduces the synchronization cost since we only transfer the data that has changed, not the full data set. With these techniques, gossip for detection, sloppy quorum, and hinted handoff for temporary failover, and anti-entropy with Merkle trees for recovery, we create a resilient, available, and eventually consistent key-value store capable of surviving real-world failures. SS table, sorted string table. SS tables are immutable, disk-based data structures that store a sorted list of key-value pairs. These are created during the flush operation when in-memory data, like the mem table, reaches a certain threshold. Key characteristics of SS tables. Sorted order enables efficient binary search and merge operations. Each SS table typically comes with an index to allow fast lookup within the file. Multiple SS tables can exist on disk, and they are periodically merged and compacted to improve lookup efficiency and reduce storage bloat. Bloom filters are probabilistic data structures used to quickly check whether a key might exist in an SS table or definitely does not exist. How it works. Each key is hashed using multiple independent hash functions. Each hash maps to a bit in a bit array, which is set to 1. When checking a key, we hash it again and check the corresponding bits. If any bit is 0, the key definitely does not exist. If all bits are 1, the key might exist. So we do a disk lookup. Together, SS tables and Bloom filters help the system balance between write efficiency read performance, and scalability, making them ideal for high-throughput, distributed key-value stores like Cassandra, LevelDB, or RocksDB. Let's walk through how data is written to and read from our key-value store system, focusing on components like SS tables and Bloom filters. Starting with the write path, when a client sends a write request, the data is first persisted to a commit log to ensure durability in case of failure. Then, the data is stored in an in-memory cache for fast access. Once this cache, often called a mem table, fills up or hits a threshold, the data is flushed to disk in the form of SS tables, which are immutable, sorted lists of key-value pairs. This approach allows efficient merging and compaction of data on disk. On the read path, if a read request comes in, the system first checks the in-memory cache. If the data is found, it's returned immediately, ensuring low latency. If not found in cache, we use a Bloom filter, a probabilistic data structure that tells us whether a key is definitely not in an SS table or might be in it. This allows us to avoid unnecessary disk lookups, significantly improving performance. Based on Bloom filter results, we scan the relevant SS tables on disk to find the key and return the value to the client. This design ensures efficient reads and writes, balances memory and disk usage, and keeps latency low.